Right now, factories in China are making solar panels almost twice as powerful as the ones on your roof. Same size, same sunlight, nearly double the electricity. The material making this possible isn't a fancy lab invention. It's a rock. Someone found this rock in the Russian mountains almost 200 years ago, and nobody cared about it until a lab in Japan tried something strange with it in 2009. For 70 years, one material has powered almost every solar panel on Earth: silicon, melted at over into pieces thinner than a human hair. It works, but it's running out of room to get better. This new material doesn't have that problem, and it's already breaking world records on production lines, with China building factories bigger than anyone else can match. The material is called perovskite. It was first discovered in the Ural Mountains of Russia in 1839, and for over 150 years, it was just a rock, studied by geologists, ignored by the energy world. Eventually scientists realized they could build new materials copying perovskite's crystal pattern using cheap ingredients plus a small amount of lead, and that pattern turns out to be exceptional at catching sunlight and converting it into electricity. In 2009, Japanese researcher Tsutomu Miyasaka built the first solar cell from this material. It converted less than 4% of sunlight into electricity, worse than cells built decades earlier. But the material absorbs light about 10 times more strongly than silicon, so a layer thinner than a soap bubble can absorb as much sunlight as a silicon layer hundreds of times thicker. By 2026, a Chinese perovskite cell hit nearly 28% efficiency, beating every single-layer silicon cell ever tested. A material that started under 4% efficiency caught up to a technology the world spent 70 years perfecting, in under 2 decades, and Chinese factories are already producing enough panels each year to power hundreds of thousands of homes. To understand why this matters, you need to know why silicon hit a wall it can never pass. Silicon is reliable, and can sit on a rooftop for 25 years without much trouble, but it has a hard limit baked into basic physics. It can never turn more than about 33% of sunlight into electricity, and commercial panels aren't even close, converting only 20% to 22.5% today. That means roughly 80% of the sunlight hitting a typical panel is wasted. For decades engineers squeezed out tiny gains through better coatings and textures, but as one solar industry leader put it in 2025, silicon has basically had all its lemon juice squeezed out. Making silicon panels is also expensive and energy-hungry. Quartz sand gets heated with carbon past 3,000 degrees Fahrenheit, purified to 99.999%, turned into a gas, regrown into a crystal, then sliced with wire saws, burning huge amounts of energy, water, and chemicals at every step. Silicon wafers account for a big chunk of a panel's total cost, and that cost has stayed stubbornly high even as other components got cheaper. The industry was stuck near a 22% ceiling with a hard limit of 33%, and the answer came from a mineral that had sat on a shelf for almost 200 years. What makes perovskite different isn't just efficiency, it's how it's made. It's not one substance but a crystal pattern scientists can build with different ingredients, tuning it for different colors of light or better stability. Silicon must be grown as a near-perfect crystal in a super-hot furnace, needing clean rooms and billion-dollar equipment. Perovskite can be dissolved into a liquid, almost like ink, and coated onto a surface at room temperature, no furnace, no clean room. A silicon factory is like a bakery where every loaf must be perfect. A perovskite factory is more like a printing press. Because it goes on as a liquid, it can be applied to flexible plastic, curved surfaces, even glass windows, and because the layer is so thin, raw material costs are tiny, changing the entire cost math of a solar panel. But early perovskite had a real problem: it was brilliant in the lab and fell apart everywhere else. Humidity could break it down within days, heat faded its performance, and even ordinary ultraviolet sunlight slowly damaged the very material built to catch it, like a sponge that dissolves the moment it gets wet. Engineers called it a lab queen. There was also the lead issue. The best performing versions use a small amount of toxic lead, tiny compared to a car battery, but still a sticking point under strict rules like those in the European Union. Researchers are developing lead-free versions using tin, though those currently underperform. while manufacturers add protective layers to contain any lead if a panel cracks. And durability remained a deal-breaker. Silicon panels carry 25-year warranties backed by decades of proof, while early perovskite could fade within months. Insiders joked it was always 5 years away from ready, for over a decade straight. Then engineers stopped trying to replace silicon and started stacking a thin layer of perovskite directly on top of it, a design called a tandem cell. Sunlight is like a buffet of different colors, and the perovskite layer absorbs higher energy blue and green light while silicon underneath catches the red and infrared light that would otherwise pass through, together capturing far more of the spectrum than either material alone. That pushes the theoretical efficiency ceiling past silicon's 33% limit, with some researchers pointing to over 45%. A typical silicon panel today converts 20% to 22% of sunlight, producing 400 to 500 watts per panel. A tandem panel has already hit 29.2% efficiency and 97 watts of output at the same industrial size, nearly double the power from the same footprint, without needing a bigger roof or more panels. Crucially, the silicon layer is made the same way it's always been made, and perovskite is simply coated on top as an added step, meaning existing factories, supply chains, and warranty systems don't need to be thrown out. Having a record-breaking lab cell means little if nobody can build it by the millions, and this is where China's role becomes central. Because perovskite can be sprayed, painted, or printed onto a surface instead of grown in a furnace, it scales fast. As early as 2023, Chinese companies reached meaningful production, and by 2025 into 2026, several manufacturers pushed into full industrial-scale production, running factories the size of shopping malls around the clock. The environmental math backs it up too, with one manufacturer's data showing this coating process produces about a third less carbon dioxide per watt than traditional silicon manufacturing, since it skips the extreme heat silicon requires. China's government backed this technology as a national priority as far back as 2021, letting researchers move lab breakthroughs into real products in under 2 years, compared to as long as 5 years elsewhere, where manufacturers must chase funding and work through regulations one pilot line at a time. Companies in South Korea, the United States, and Europe are chasing hard with their own tandem designs, but they're starting from behind, while China's factories are already running and its costs are already dropping through scale. For 70 years, getting more power from sunlight meant squeezing tiny fractions of a percent out of a crystal that was always going to hit a hard wall. Now a rock ignored for over 150 years is layered on top of silicon to blow straight past that wall, capturing more sunlight with a fraction of the material, less carbon, and power numbers that would have sounded like science fiction just 5 years ago.